Well, today's question is, how did life emerge on our planet? How was it possible? And that is the biggest problem in big history for several reasons. First of all, the big question is, how could all this very complex life, it is very complex, all these biochemical reactions that are happening all inside of us and all the other living things, how could it have emerged out of far more simple chemicals? You would expect exactly the opposite, that more complex things would break down. Yet, apparently, all by itself, spontaneously, life emerged out of more simple things. How did that happen? Second problem is we don't have any hard data. Zero. Nothing. That's a big problem in big history because we need our empirical evidence, right? And that leaves a lot of room for speculation. So what I'm going to talk about now is speculation based on some empirical evidence that may help us to understand how life may have emerged on our planet. What are the current hypotheses for the emergence of life? Well, first of all, spontaneous generation, as I said, that happened all by itself. We don't expect that a creator was behind it. We cannot be sure, but that's the assumption in science. And we also think it happened a long, long time ago. It doesn't happen every day, for example, in whatever stew we might find or anywhere. It happened a long, long time ago and for very specific reasons. And we don't know where it happened. It might have happened here on the planet, and that is the most popular idea. But it might also have happened somewhere else in the universe, and then it arrived here in whatever ways it could have arrived. It might have rained down from the universe. It might have arrived inside meteorites. We simply don't know. It is entirely possible. We don't know. But if it emerged somewhere else, then we basically have to answer the question of where did it emerge and how did that happen? So we're basically moving the problem somewhere else. But let's focus now on the hypothesis that it emerged here on our planet. And before we start talking about that any further, I would like to tell you a little story about my experiences. In the 1970s, so a long time ago, I studied biochemistry. And this is the biochemistry lab at Leiden University where we did that. And I was involved in a research group that studied this problem. There are certain bacteria, and this one is called Agrobacterium tumefaciens, and this bacteria is able to infect plants and cause, let's say, the specific growth not regulated by the plant itself or the tree. You see such a tree in the Sarpeterstraat in Amsterdam with a big cancer on it. And cancer means the breakdown of the regulation of cell growth according to, let's say, the plan as defined by the genetic material. And it turns into a big ball, and a big ball, what is it doing there? It is actually producing food that the bacterium likes. So the bacterium is regulating the tree to, instead of doing what it wants to do for itself, if you can say such a thing for a tree, into producing food for itself. So, and it does so by putting its genetic material, at least a little bit of its genetic material, into the tree, and as a result the tree starts to do different things. Well, it's very interesting that the genetic material of a bacterium can actually change the behavior of a tree. Apparently, the molecular mechanisms underlying all of that must be very similar, because if not, it would never work. So what does that point to? It points to very similar biochemistry in very many different ways, because it's all very complicated and tiny changes may already wreck the mechanism. So very simple, similar mechanisms that apparently tell us that they must have a common ancestor. That is what it means. There must be a common ancestor between bacteria and plants. And if you start thinking about it, there must be a common ancestor about all life forms. And you can do a very simple experiment. You can just eat a banana. Why is it possible? How is it possible that you can actually digest that? Apparently the building blocks of a banana are similar to our building blocks, otherwise it wouldn't make any sense for it to work. Just try to eat a rock, for instance. That doesn't work. So apparently rocks and humans have not a common ancestor, at least not in terms of life. Their common ancestor is far more back in time in stars that exploded and provided the more complex chemical elements, but not in terms of life. And that is true for all life forms. Basically, everything can eat, all the animals that can eat plants, they can do so because they have a common ancestor. Right? So can we trace that common ancestor? And the answer is yes, you can do that by comparing all the different genetic materials, all the different forms of DNA, assuming that they changed over time more or less regularly. And then you can look at how similar they are or how different, and you can construct a family tree as a result. And a family tree points to a common ancestor about 3.5 billion years ago. So before that time, life must have emerged at a certain point in time. Now, what do we know in terms of fossils? Well, we have fossils that are almost as old as that. The famous stromatolites, let's say the modern ones, are still living in Western Australia in a shallow bay close to the sea. In fact, they are little tiny bacteria sitting on rocks and trying to harvest whatever they can in that situation. And here on the left we see stromatolite fossils that you can find in the Rocky Mountains. And that indicate that there has been a continuity of these life forms of over 3 billion years. That's really a long time. 3 billion orbits around the sun. That's what it means. So apparently these life forms must be fairly close to what we can think of as the origin of life, but they cannot be the origin itself because they're way too complex for that. So how can we think about how all of that would have originated? First of all, you want to know where did the chemical building blocks come from. And they may have come from outside. They may have rained down on us with the aid of comets, meteorites, and whatever happened to reach the early Earth. And it seems like a very serious option, because out in the universe you can measure simple chemical elements. You can observe them. So if they are there now, they probably rained down on us earlier as well. But they may also have formed on our planet itself in watery environments, especially volcanic environments. So it may be a combination of both. Now, what do you need for life? First of all, you need to be able to replicate. Without replication, very soon life would come to an end. But you also need to keep your old biochemistry going, and it's pretty complex. That's called metabolism. So you need all of that in order to keep life going. Now, which molecules do you really need in simplified forms that could do all these jobs? And there's one chemical, it's called RNA. I won't explain what it is. It's somewhere in between DNA, let's say the blueprint of life in terms of genetics, and all the workhorses that are in the cells, like the proteins. But it does really a lot. It's like the Swiss Army knife of a cell, you could call it. It does very many things. And as a result, scientists think that quite possibly life originated with molecules that more or less look like RNA and then evolved from there. And where would we find these circumstances? You would find them in oceans, in watery environments where lots of chemical reactions are possible, near undersea volcanoes where there's a lot of stuff coming out that you could make life from, where there's a lot of energy coming out that can help you push things from being less complex into more complex. And you find these clays that may provide a good frame for forming little cells. And you can expect that on the early Earth, there was more volcanism because the Earth was still hotter, so more stuff bubbling out, so to speak, from below. So the circumstances would have been better for forming life. Now, if that's the case, you can still wonder whether life would still be forming in such situations. And who knows? We cannot really be sure. But the difference with the origin of life and the situation now, that there is a lot of life around that may gobble up any new life that's forming. And that may point also to an early competition between possible early life forms that led to the elimination of most and the survival of only one life form that in the end gave rise to all of us. Well, we don't really know. These are hypotheses, scenarios. Nothing is certain yet, but what we do know for sure is that life did emerge and that there's a real great variety of it right now.